Welcome to lecture number 2. This lecture will be about combinations. To recap so far, what we have done so far. So last lecture we looked at ordered choice. So we looked at choice with replacement and without replacement. Okay, so ordered choice means that it matters which one we choose first, which one we choose second, and which one we choose the kth. And with replacement means that once something has been chosen, for example 1, it goes right back to be a candidate for a choice again. Without replacement just means that it cannot go back. So once you choose something like 1 without replacement, then it's done. You cannot choose it again as a choice. And therefore, we looked at deriving two formulae. One formula was n to the k, which is how many ways are there of choosing k from n, so given n objects k with replacement, and n permute k, which is nothing but n factorial divided by n minus k factorial. We derived this as well. And this is n permute k, the number of permutations of n with k, where permutation is an ordered choice without replacement. In this lecture, we look at a combination. A combination is still n distinct objects, so we have n distinct objects to choose from. Okay, and yes, but the order of choice doesn't matter. So if you choose in the order, for instance, 1, 3, 2, 4, it's the same choice as 4, 3, 2, 1. It's the same choice as 1, 2, 3, 4, and in fact it's better to write a combination as a set 1, 2, 3, 4, because we know that in a set the order of the elements does not quite matter. And one more thing to note is that choice cannot be repeated. So it makes no sense to say 1, 1, 2, 3 as a choice, because 1 cannot be repeated. So if you want to choose 4, it has to be 1, 2, 3, 4 or 1, 2, 3, 7. You cannot repeat an element in your choice. So the question is, how do we count these combinations? And there is a very simple trick, as we showed in class. Let's take an example of a problem. Suppose we have 10 people, P1 through P10, and we would like to select 3. So n equals 10 and k equals 3. Okay, so question is, how many ways are there to do this choice? Now there is a trick, and we assume temporarily that the order does matter, temporarily, mind you. And the question is, how many choices are there? If the order does matter, we know we have already seen how to do this, and the answer in this case is 10 permute 3 or 10 factorial by 7 factorial choices. Okay. Now let's roll back our assumption that the order matters. And what does rolling back mean? Well, rolling back means that we have to look at how many ordered choices, and these are ordered choices, mind you, collapse onto an unordered choice. So we want to say how many ordered choices collapse onto the same unordered choice. So in this case, if you look at this, you have one, suppose you have a choice P1, P4, P8. There is 6 ways of ordering them, okay, and all of them collapse onto a single choice, the set P1, P4, P8. So whatever the answer is, we divide by 6, and this is n10 P3 by 6, and that's the answer. And note that we get 6 because there are 3 factorial ways of ordering 3 elements among themselves. Right? Then the same trick works for a general n and a k. So suppose now we have n objects, O1 through On, and we would like to make k unordered and without replacement choices. So that's a combination where we have n objects and k choices. Okay. So assume again that the order temporarily does matter. How many choices are there? We already saw this in our previous lecture, and the answer is n permute k, which is n factorial by n minus k factorial. Very good. And then moving right along, we say how many ordered choices collapse onto the same unordered choice. And if you do the math again, you have k factorial of these ordered choices that will collapse onto the same unordered choice. So whatever the answer is, npk for the ordered case, we divide by k factorial, And if you want to write this out, this is n factorial by n minus k factorial, okay, and that's the answer. So the answer really is the number of combinations. We write this in one of two ways, nck, or this funny notation where you have a bracket, n and a k, okay, and this is called the binomial coefficient. N is the number of objects, k is the number of choices, or nck is another way of writing the same binomial coefficient, and the formula for that is n factorial by n minus k factorial, k factorial. Okay, so simple question: how many ways are there of choosing a team of 6 players from a total of 15? The straightforward answer is 15 choose 6. N equals 15 and k equals 6. We are just talking about a team, so we aren't distinguishing the players, so it's just a set of 6 players. And if you put this all together, this is an unordered choice without replacement. Answer is simply 15 choose 6. Here is a more interesting problem. Consider an n cross n grid, just like in Manhattan. Okay, and our goal is to get from here, the 0, 0 point, to n, n point, and we are allowed to traverse along the grid, so we are not allowed to take a diagonal. So the question is, how many ways are there of going from 0, 0 to n, n? So let me give you 2 examples of how we would go. Here's path number 1. Path number 2 is like that. And let me show you another one. Okay, so the question is, how many ways are there of going along this grid from 0, 0 to n, n? So that's 1. Alright, this sounds like a tall order counting this, but actually there is a very simple trick. Now, if you want to go from 0, 0 to n, n, I can convince you that there are 2 n steps that you need to take, where each step is going to the right or going up. Okay, so and among these 2 n steps, you need to take n moves to the right, and you need to make n moves up, and you can interleave them whatever way you want. So any path is specified by go right, go up, go right, go right, go up. And what you need to do is you need to make a total of 2n, of which n have to be right and n have to be up moves. And the answer, once you think about it in this way, is really simple: 2n choose n. So you have 2n moves to make, of which you're choosing n of them to go to the right, or equivalently you're choosing n of them to go up. Okay, so the last question is, count the number of 2n plus 1 bit strings with more zeros than ones. So this is again a problem of counting, and we'll see how this count can be done. So if you have 2n plus 1 bits, so this is bit number 1, bit number 2, 3, up to 2n plus 1. Okay, and we would like to have more zeros than ones, which means that you can have many cases. So you can have n plus 1 zeros and n ones. Okay, and this case can be done in 2n plus 1 choose n plus 1. Why is that? Because you have 2n plus 1 bit positions, of which n plus 1 can be zeros. Now if you count this way, you get the following answer. So you get the answer which is like this. So you get, okay, I can have n plus 1 zeros, so I can have 2n plus 1 c n plus 1. I can have n plus 2 zeros, so it's 2n plus 1 c n plus 2, 2n plus 1 c n plus 3, and this is a summation all the way from 2n plus 1 c to n plus 1, which says all of them are zeros. So this is the answer. It's a summation, and in the next lecture we'll convince ourselves that the answer to this summation is 2 to the 2n.